Hello everyone, my name is Jeremy Park, and today I'll be presenting the introduction to our project called Sleepy Time. Roughly 50 to 70 million people in the US suffer from a chronic sleep disorder. And it's likely more than this, as most sleep disorders are not even identified or treated. This is truly a public health crisis, as the lack of sleep has been shown to increase the effects of depression, heart attack, obesity, hypertension, and many other health complications. Since sleep is so foundational to our health, when our sleep suffers, many other areas of our health suffer as well. Currently, the gold standard for studying sleep is the polysomnogram, or PSG. This is when you get wired up and they measure your brain activity, eye movements, muscle activity, heart rate, and other events such as snoring. In the dataset that we'll be using, 5 different sleep stages were manually classified at 30-second epochs, and events such as sleep apnea are also recorded. The goal of this project is to improve the deep learning methods that can automatically classify these sleep stages in PSG data. To automate this sleep stage classification process would enable much more efficient sleep pattern analysis, as currently researchers are manually annotating 30-second periods of sleep. And to automate this would hopefully lead to improved public health. This project also supports current research at NC State involving the innovation of AI-driven sleep technology.
So our dataset comes from a medical institution called Hakoden's Medisch-Zentrum. And so this sleep database consists of 154 patients, 88 male, 66 female, who are all randomly sampled from a population of adults who suffer from variant sleep disorders. And so from each patient, they've recorded 8 sensors at 256 Hz, which are 4 EEG sensors, 2 EOG sensors, 1 EMG sensor, and 1 ECG sensor. So when observing our data, we found that a typical night ranges from around 7 hours to 9 hours. So in terms of our class labels, annotations have been marked by sleep experts with 30-second epochs to classify the scores of sleep patterns into 5 stages. And so these 5 stages are stage W, stage N1, stage N2, stage N3, and stage R. So here's an image of the class distribution of the data that we're working with. So you can see on the left that N2 accounts for about almost a third of the entire dataset, while N1 only makes up about a tenth. So looking at the class imbalance, we expect to see our model to be more skewed towards N2, just because of its proportion. And so to combat this, we may use something like class weights to compensate for the imbalance. And so for our methodology, we intend to experiment with different state-of-the-art techniques like CNN, LSTM, or maybe a combination of the two to see if we can produce a model that can classify the 5 sleep stages based on this data set. And so for our data format, we've decided to use a window of 2 seconds with a stride of 2 seconds so that there is no overlap between the windows.
For our baseline model, we chose to use a support vector machine, or an SVM. These are commonly used in EEG classification tasks for comparison, as they perform well at distinguishing features from EEG data. And since our dataset consists of EEG, EMG, and EOG, we felt like it would be a good step. The proposed model that we use here is a hybrid convolutional bidirectional gated recurrent unit model, henceforth referred to as the CNN GRU model, because that's a bit of a mouthful. But we hope that the GRU layers would improve a time series understanding, whereas the CNN would improve the temporal sensitivity of the feature extraction. For validation, we've used categorical cross entropy as our training metric. However, we primarily examined the weighted F1 score to account for the class imbalance. We used confusion matrices to visualize the model performance. Our results can be seen right here. So for the SVM performance, we saw a training F1 score of 57.58% and a testing F1 score of 34.94%. So a little over 20% delta due to overfitting there. And we can see in the confusion matrices, there's really not much of a clear trend. It looks like you mostly guessed primarily W and N2. However, for the CNN group architecture, we saw a training F1 score of 72.36%, however, testing F1 score of 62.23%. Still overfitting slightly, however significantly better, and we can see that much more clear diagonal line. Some of the obstacles we ran into was that EEG data is just notoriously difficult to generalize, and that kind of makes it difficult to actually create a model that does not overfit. The class imbalance was a bit of a problem, however, the class weights and the F1 score are pretty effective at that, and we were able to use data generators to resolve the issue with too much data that we weren't able to load into memory on Colab at once. We did have one mistake where the original data processing approach actually led to a spoiling of the test set, and that was a problem. And we have resolved that now, and that accounts for why our early results were actually better than our current results. For future scope, we really could probably eke out a little bit more performance here, and using some more powerful, longer running compute services as opposed to Colab would greatly aid that training and tuning process. Here are references. Thank you.